This conference will now be recorded.
Very good evening, students. Today we'll be completing this magnetism chapter by solving few problems. These are all actually from JEE Mains 2019. Paper. Okay, so this first question which we are seeing here, it is related to galvanometer. Let us see. So a moving coil galvanometer has a coil with 175 turns and area 1 centimeter square. It uses a torsion band of torsion constants 10 to the power minus 6 Newton meter per radian. The coil is placed in a magnetic field B parallel to its plane. The coil deflects by 1 degree for current 1 milliampere. The magnetic field is approximately how much in Tesla? That we have to calculate. So let us solve this problem. So it is actually from the basic theory of galvanometer. So how galvanometer pointer gets deflected, etc. So there should be a coil, and the coil end of the coil should be connected to the pointer, and there will be some springs. So that springs actually are called torsional bands over here. So those have some torsion constant. When the coil will rotate in the magnetic field, the this torsion bands will actually experience a torque that will give a counter torque to uh, the coil in the magnetic field. So when the torque in the torsional band and the torque experienced by the coil becomes the same, then there will be an equilibrium situation. Now that is the maximum deflection. Let us say that deflection is phi, and it has the torsion band has torsional constant some c. So c phi is equal to the torque experienced by the coil, and that torque actually is given by m cross b. What is m? M is actually a magnetic vector. Like this is a vector quantity that is, it is called magnetic dipole moment or magnetic moment, and b is the magnetic field induction, as you know. So m is actually given by I into a. So here the current is not a vector quantity, but the area is a vector quantity. In the sense, suppose you have a plane like this, a coil like this will have uh, this we can say area vector, where the magnitude is the area of this coil, and direction will be actually outward normal to this plane, outward normal to this plane. So here this coil has 175 turns, so I can write this n is equal to 175, and area is given as, magnitude of the area is given as 1 centimeter square. That means 1 into 10 to the power minus 4 meter square. Okay, because 1 centimeter means 10 to the power minus 2 meter, and square of it, that square of it is 10 to the power minus 4 meter square. And b we have to find out. So here there are two things again. The coil is deflected by 1 milliampere current and deflection is 1 degree. When the 1 milliampere current is flowing through the coil, then the deflection of the coil will be 1 degree. So okay, so let us find out first what is M. So M is, let me find out the magnitude itself. M is I into A, that means total current, that is I into N. This is, see, in one turn there is I current, so in N turns there will be N into I current. Okay, so this is N into I and this is area. So this will be M. This is the magnitude of the magnetic moment. And see, as I said, here the magnetic field is actually parallel to the plane. So if this is the plane, then parallel to the plane, the magnetic field is applied. That means the magnetic moment, the area vector is actually perpendicular to the magnetic field. This is magnetic field, this is area vector. So if we just now write it here, what is torque, then magnitude of the torque will be, mb sine 90 degree, so 90 degree is 1, so mb. So m is again n I a and this b is b, so torque is NIAB in this case. Okay, so there are informations given in the problem. We have already noted down some of them. So area is given, already we know. N is given, that is 170 turns. Now what we'll do, we'll write what is torque. Torque is N is 170. Okay, let me just go with this itself, this equation C phi. So phi is 1 degree when current is 1 milliampere. So that is what we'll be actually plugging now. So we have got torque NIAB. So this we will write NIAB is equal to C. Torsional constant is already given. C is actually 10 to the power minus 6 Newton meter per radian. So we have to actually find out B. B is equal to C into phi divided by N, I and A. C is given 10 to the power minus 6 and phi is given 1 degree. 1 degree means, see, pi by 180 will be 1 degree. So this is in radian. So we have got C and phi over here. Now I'm not writing the units because the units will come. If I go with a single unit, then all the units, like, it will get in Tesla. Okay, if we go by SI unit, so N is 175 and this is 1 milliampere. Since I have used 1 degree deflection, so the current is 1 milliampere when the deflection in the coil is 1 degree. So this is 1 into 10 to the power minus 3. This is yes. Now area is 10 to the power minus 4 again. Okay, this is, so this should give you in this should give you unit Tesla. I can just write it here, Tesla. This is Tesla. Now if we just do the calculation, see, this will be 10 to the power minus 6 plus 10 to the power 7 and again here 180 into 170. Okay, so if we solve it, look here, it will be pi into 10 into 180 into 175. Okay, this is going to be Tesla. Now look here, this 10 goes with this. So this, if I, okay, let me tell you this is 3.14 and this is 18. So let me take approximately this as 3. So it will give you 18,175. So this will give you 6. So basically B is 1 over 5, 6, 30 and so this is uh, approximately 1 over 1000. Okay, that means this is approximately 10 to the power minus 3 Tesla. Okay, so the magnetic field we have found out what approximately 10 to the power minus 3 Tesla. So you have to just remember this thing for a galvanometer coil. Tau is equal to C into phi, where C is the torsional constant and phi is the deflection in the coil or in the pointer, angular deflection obviously, and then you have to write this torque and corresponding parameters. You have to see whether the values are given or not, and that's how we have reached to this solution. Okay, move on to the next problem. This problem is also actually given JEE Main 2019. In 2019, let us read the problem first before we solve. The problem states that a conducting circular loop is made of thin wire, has area 3.5 into 10 to the minus 3 meter square and resistance 10 ohm. It is placed perpendicular to a time dependent magnetic field which is given as this. Excuse me. I'm sorry, there is a background music. I hope. I don't know whether it is audible, madam. Is it audible? I am actually helpless today because there are excuse me, there are some puja and people are excuse me, people are actually enjoying with this mic. I can't help. I have actually logged everywhere. Still, may this background music may come. Anyway, today we are solving problems, so that would not distract us too much. So conducting circular loop is made of thin wires, and wire has radius given here. Thin wire, no, not this. This is circular loop has area. Sorry, area this. The loop area is this, not the wires. And resistance is given. It is placed perpendicular to a time-dependent magnetic field. I'll write the time-dependent magnetic field. Vt is equal to 0.4 Tesla into sine 50 pi into t. So the field is uniform in space. So there is no space variation. It is only time variation. So that's why this amplitude term is constant. The net charge flowing through the loop during t is equal to 0 second and t is equal to 10 millisecond. That means you have to find out the charge what is flowing through the coil during this time interval. So what is the time interval? T1 is 0 second and T2 is 10 millisecond. Millisecond means 10 into 10 to the power minus 3 second. Okay, during this time interval, we have to find out how much is the charge flowing through the conducting circular loop. So the conducting circular loop actually is kept in a uniform magnetic field, and then magnetic field is actually varied with respect to time. So what will happen? What do you expect when a circular loop or any kind of loop is kept in a magnetic field, uniform magnetic field? There will be flux linked. Okay, flux linked. If the magnetic field is varying with time, then with time the flux also will vary. So we know we'll get EMF. See, see, EMF we know from this Faraday's law, d phi by dt, or we can write area into B1 when t is equal to 10 millisecond minus B2 t is equal to 0 second. So this is the change in the flask, time rate of change in the flux. And this would give you what? This would give you the EMF, right? So we know the flow rate of charge. Rate of flow of charge is actually current. So rate of flow of charge is equal to current. So we have to find out actually current during this time interval. Already we are seeing the change in the that means the rate of change of the flask. So we are indirectly getting flow of charge during this time interval. Okay, flow of charge means the current you have to find out. Okay, so this is the fundamental concept over here being used. So flux will be linked with the circular coil. That flux will change because the magnetic field is changing with time. If flux change is happening, there will be induced EMF. Okay, and that induced EMF, since there is a resistance given over here in the coil, so that induced EMF will produce a current, and that will flow in the coil. So net charge flowing through the loop during this time we have to find out, and what we can do is we can find out the flux change in the flask divided by the interval of time, sorry, divided by the resistance. So charge flowing during this time will be d phi change in the flask, okay, divided by r. So this is the point here. This actually, this I mean to say d phi by delta t. Okay, I'm sorry, d phi by delta dt. So I is equal to d phi delta phi by delta t. Okay, so q means I into delta t. Okay, so I into delta t, that means d phi by r. You have to basically find out the change. So this dt you don't have to change, don't have to write here, because d phi by dt by r is equal to current, and if you multiply delta t both sides, so it will be delta phi by r. So this will give you the total charge flowing during that particular interval of time. Okay, if you are confused, I write once again. See, I means EMF by r is the resistance. EMF means what? EMF means d phi by, I'm writing delta phi by delta t by r. So I need to find out current. Current means I into delta t. So that means I'm just taking magnitude. So d phi by r. So this is the way I'm arrived here. Okay, I have arrived here in this way. Anyway, you are must okay, you must understand this. All right, now we'll just try to put all the values. Let me go to the next page. Okay, okay, we'll just write down the parameters first. Okay, so we have to find out d5 first. Okay, so d5 means what? B, change the B into area. Anyway, area is constant. So how much is the area? The area is being given. Area is given as 3.5 3.5 into 10 to the power minus 3 meter square. Okay, and so this dB change in the magnetic field will be B when t is equal to 0. T is equal to 10 to the power minus 3 second, and B when t is equal to 0 second. Okay, so this is B. Uh, delta B change in the magnetic field, and area 3.5 into 10 to the power minus 3. Okay, this is the flask. So B was given as 0.4 Tesla into sine 50 pi t. Okay, now let me find out when t is equal to 0. So this will be 0. Okay, because the t is equal to 0 means sine 0 0. When B of t is equal to 10 to the power minus 3, let us see what happens. 0.4 Tesla into 10 to the power, into sine 5, sine 50 pi into 10 to the power minus 3. Okay, that means 0.5, 0.4 sine of 50 divided by 1000 pi. Okay, so this is yeah, so we can find out. It should be, okay, so it is actually 20. No, just there is some mistake I have done. I think in the expression of the magnetic field I might have done some mistake. Let me check. Okay, this is not 50, this is 0.5 into t, so pi t. Okay, so in the expression of the magnetic field it was actually 0.5 pi into t. Okay, I'll just write over here 0.5, not 50, 0.5 pi t. Okay, so t is now this. Let me go over here. This is not 1 millitesla, this is 10 millitesla. 10 millisecond. So then it will be 10 to the power minus 10 to the power minus 2. Okay, this is 10 to the power minus 2. I think this is okay now. Even with 50 also will go with that. Okay, so in the question, what was there? Okay, let us. So this is 10 millisecond. This is 10 into this means 10 to the power minus 2 second. Okay, this is where we had done some mistake. Okay, let me just clean this portion. Rest of the things are okay. So here it is 50. So b t is equal to 10 to the power minus 2 second. We'll get zero point 0.4 sine of 50 pi t means 10 to the power minus 2. Okay, so that would give you, sorry, this is 4 sine of 50 by 100 pi. Okay, so this would give you, this is whole Tesla, so 4 into sine of pi by 2. Okay, pi by 2, so this would give you 0.4 Tesla. Okay, so you have got 0.4 Tesla minus 0 Tesla, so this would give you 0.4 Tesla. So you have got already d phi. Now if you remember, we have we have to actually find out charge flowing during the time interval 0 and 10 millisecond. During that time interval, we have to find out the charge flowing through the coil. So the charge is actually, sorry, charge q charge q during that time interval will be d phi by r. Okay. So d phi we have got 0.4 Tesla. R was given, I think, 10 ohm. So 10 ohm. Okay, 10 ohm. This will give you, let us see how it is. There was A also over here. This I have not multiplied, so we'll multiply A also. A by R. Oh, so A is actually 3.5 into 10 to the power minus 3 meter square. Okay, so now it will give you correct answer. So 435, let us say, and this 1 so the here will be 10 to the power 3, 10 to the power minus 3. This will be coulomb in coulomb. So into 10 to the power minus 6 coulomb. So this is 1 140 140 coulomb. That means into 10 to the power minus 6. Okay, so this will actually give you, if you go with milli coulomb, then let me check. There are some power problem. This is 10 to the minus 3 anyway. Fine. This is ohm, 10 to the minus 3, 3.5. Okay, that's fine. It's all right. Actually, this will give you 14 millicoulomb. Okay. So this is the answer here. This is the option. Okay. See, if you want to make it millicoulomb, you have to you have to multiply with 10 to the power 3. Okay, 10 to the power 3. That's how you will get 14 millicoulomb. Okay. So the 14 millicoulomb, this is the correct answer. I hope you have understood this. The net charge flowing through the loop during this time we have calculated, and that we have used to calculate this. We have used this formula. Okay, d phi by r. So we have to change. We have to find out the change in the flux and divide that with the resistance of the coil. Okay, we'll move on to the next problem. This is another interesting problem. This is very easy. So a charge particle carrying charge 1 microcoulomb is moving with velocity this. So let us see. The velocity is 2 I cap plus 3 j cap plus 4 k cap. Okay, this is 3. 3 j cap plus 4 k cap, and this is B 5 I cap plus 3 j cap 6 k cap into 10 to the power minus 3. This is B. Okay. So a charge particle having charge 1 microcoulomb is moving with velocity this meter per second. If an external magnetic field B exists in the region where the particle is moving, then the force on the particle is given F into 10 to the power minus 9 Newton. So what is this F vector? So this is a magnetic force. Basically, magnetic force we write Q into V cross B, right? Q into V cross B. So Q is anyway given 1 microcoulomb, 1 into 10 to the power minus 6 coulomb. Now let us do this cross product V cross B. Here we'll be using our cyclic rule which we have learned in the vector in case of cross product. Okay, so let's write here 10 to the minus 6 coulomb into this I 2 I, so I cross I will be 0, first term is 0, then along with this Ij is 90, so this is fine. So 6 Ij, see I, J and K. Cyclic rule, when you go clockwise, I cross J will give you K cap. Anti-clockwise direction will give you negative of the unit vector. So this is 2 I into minus 6 K. So the magnitude of this product will be, cross product will be minus 12. And along with that, see this 2 I cross K. I cross K will give you minus J. Okay, minus J cap. So 3 terms gone. So like that, this will give you J I mean minus K. I'll write directly. I'll write directly here also. It will be plus 12J plus 12J. Now this with this Ji is minus K. So 15 minus K cap. J will give you 0 and JK will give you positive number. So this is, and finally we'll do the addition and subtraction etc. So with 4 Ki will give you J. Okay, K cross I will give you J, K cross I, so 20 J cap this with this, k j will give you minus I, 12 minus I, 12 minus I cap, and kk will give you 0 again. So if we solve it, like use the knowledge of vector addition, with the same component we can do the subtraction and addition. So this these are k. So this is 18, the 33, and from 33 you have to subtract 6. That means minus 26, 27 k cap. 12, 20, 32. So it will be 32 j cap. Now I cap. I cap is only one is here. So that is minus 12 I cap. Minus 12 I cap. We need to check once again because the options are not matching with our this. Q into V cross B. Okay. That is 10 to the minus 3. B is 10 to the minus 3. So it will be 10 to the minus 9. Yeah. B was 10 to the minus 3. Okay. This would give you 10 to the minus 9 Tesla. That's fine. Only this part we have to find out. So this is 12 minus 12 I cap. Let me check whether we should get some, or we'll directly do B cross B to cross check. You can do it in the determinant form also. Let us cross check with determinant form ijk. Okay, so B cross B, that means components of B we have to write first. So components of B are 2, then this is 3, this is 4. Then components of B we have to write 5, 3, and minus 6. Okay, along with that 10 to the minus 3, you can write 10 to the minus 9 over here, doesn't matter, 10 to the minus 9 into this. So I cap will give you this. So this is minus 18 minus 12. I think there was some mistake in the first calculation. So this is actually better to do instead of doing in that way. So here you will directly get, so minus j, you will get minus 12 minus 20. Okay, plus k cap whole into 6 minus 15. Okay, now if you do the simplification, this will give you minus 30 I cap. With j you'll get plus 32 j cap, and with k you'll get minus 9 k cap. Okay, so look now the options. Let me just erase this part and write down what we have got. I think there were some mistake in the multiplication here, vector multiplication. So we have got minus 30 I cap plus 32 j cap, and with k we have got minus 9 k cap. Along with that 10 to the minus 9. Okay, this is the in Newton. Okay, so this factor is already there, so we had to find out this. So you look this 32. Okay, 10 to the power minus 9, 3 microcoulomb. Okay, 10 to the meter per second. Everything is fine. So now see, if we want to match with the options. This is one option which is actually matching with us, and we need to check. This is actually 10 to the minus 3. This is microcoulomb, 10 to the minus 9. Sorry, minus 6. So this will give you 10 to the power minus 9 anyway. What is given here? 10 to the minus 9. That would microcoulomb. Fine. This is 10 to the minus 6. B into 10 to the power minus 3 again. Fine. So this should be actually, I don't know whether there are some options like that. Let me check whether I have typed it wrongly. Yes, I have typed it wrongly actually. There will be this one. No, sorry. Here, this is fine. Here there will be no point. Okay, this will be for whole 32. Okay, this will be the option actually. Okay, so I have just typed it wrongly in the options. So this, if you check in the original question paper, you will get this option. Okay, so better to use the determinant form of cross product. It was very simple, but because of some calculation mistake, it took long time. But in the exam hall, you must be able to do it in a minute. Okay, now we'll check with this problem. So here there is a rigid square. Let me first give you the options here. Okay, so there are options: repulsive and equal to, repulsive and equal to, equal to, equal to mu0 I1 I2 by 2 pi. First option. Second option, attractive and equal to, attractive, attractive and equal to mu0 I1 I2 by 3 pi. Then you have option C 0, option D repulsive and equal to, repulsive and equal to, sorry, equal to mu0 I1 I2 by 4 pi. Okay, so these are the options. Let us now read the problem. A rigid square loop of a side A, this is A, this is A, this is A, as you see from the figure. Okay, see, it is actually the square loop. Each sides of the square loop is carrying current I2, and it is lying on a horizontal surface near a long current carrying wire, which is carrying current I1 in the same plane as shown in the figure. You can just think that this coil is just lying on the table, horizontal table, and this wire also is lying on the table, but they are actually separated by distance a from this first side, this side. I can just give a name to this. If I say this is A, B, let me say C and this is D. Okay, so this ABCD loop is carrying current I2. It is near to another long current carrying wire which is carrying current I1. So obviously you know that this current carrying in long wire will make a magnetic field or produce a magnetic field near its region, like near both side, and the direction of the magnetic field will depend on the direction of the current. For this case, if you apply right hand thumb rule, so magnetic field will be inward here and outward over here. Okay, this will go into the plane, and here magnetic field is coming out of the plane. Now you look the direction of the current carrying loop in each side. So when we have a current carrying loop in a magnetic field, it will experience this current carrying wire will experience a magnetic force Q V cross B. So that Q into V cross B, that is for a single current charge, but for a current carrying wire, suppose uh, it has length L, okay, and it is carrying current I. So I L cross B, this is the magnetic force on current carrying wire. This is the magnetic force I L cross B. So it is a cross product, so there will be a direction, definite direction, and that direction can be obtained from right hand thumb rule. You can see this is the direction of the current, okay, direction of the current, and the magnetic field is in the plane of the paper, into the plane of the paper. So the magnetic force on this particular AD side will be in this way, okay, this force. Okay, how do you find out the force? We have got the direction anyway. Let me tell you, this is force F1 suppose, or force FAD. Direction we have got, we will just deal with the magnitude now. Magnitude ILB, here ILB suppose. So what is L? L is the length A. What is I? I is the current in this particular side AD. And what is the magnetic field? Magnetic field carrying a magnetic field produced by this current carrying wire. So that is mu 0 I1 by 2 pi A at A distance away. And this I is I2 into L is A. So this is the force, magnetic force FAD. So let us say this is FAD. FAD. So at this side also there will be magnetic force due to this current carrying wire on this BC, where there will be force in this way. Okay, this way the force will be. Okay, but one thing you have to see, this distance is now, this is actually A, this is A, this is 2A. So the magnetic force FAB will be exactly opposite to FAD, but magnitude wise FAB will be much weaker because it is mu 0 I1 by this A will get cancelled, so this will be 2 pi into 2A. 2A A get cancelled, so this, so you'll get actually mu 0 I1 I2 by 4 pi. This is actually the magnetic force, okay, magnetic force on this side, okay, FAB and F. So this is, see, FAB, as I am saying, FAB is, see here, mu 0 I1 I2 by 4 pi, but in case of this FAD, mu 0 I1 I2 by 2 pi, 2 pi, this is what, okay. So resultant force will be there will be a resultant force between AB and AD, okay, FAD and FAB, there will be resultant net force. Let me check with this. So FAB is actually less than FAD, that's why there will be a net force. Since this is FAD, let me go to the next page then. So FAD is greater than FAB, okay, then we will get a net force towards uh, A to B, towards A to B, or away from the wire, which is away from the wire. So away from the wire, from the wire. So this is mu0 I1 I2 by 2 pi, and mu0 I1 I2 by 4 pi. If you do the solution, you will get mu0 I1 I2 by 4 pi. Okay, this is away from the wire. Okay, away from the wire, that means it is kind of repulsive force. Anyway, now we have another two sides like BC. See, this is CD and this is AB. What about them? Whether they will experience force? Obviously, they will experience. But you look, these wires are actually each point, this corresponding to this point corresponding to this point. That means actually they are equal distance away, from each other. That's why if the magnetic force work in this way, in this way, both will be equal in magnitude and they will cancel each other. If I am not able to make you understand there, let me make you understand here. See this, the distance of this wire, this was CD wire, and this is AB. At each point, if I consider this point, there will be a corresponding point here. So here magnetic force will be this way, here this way. Okay. So these two forces are equal in magnitude because they are equal in distance from the current carrying wire IO1. Okay. So that's why the magnetic forces on CD and AB are equal in magnitude but acting opposite to each other. That's why they will actually balance. So no net force uh, for this. Actually, FCD minus FAB or vice versa will give you 0 because they are equal in magnitude. So net force, then ultimately the net force will be in which way? The net force will be actually, the net force will be away from the wire. So there will be net force in this direction. Okay. So this is away from the wire. So as if this wire is repelling this square. So there will be, see this one. This force is actually repulsive and equal to this. Okay. This is the answer. Okay. So this is how you have to analyze and choose the correct answer. For today, we'll stop it here. We'll next class we'll start with a new chapter. I think that is induction part. There will be induction part, AC current, etc. will be starting in the next class. Okay. So bye for today. Thank you for your patience.